Alright, so question number 9 here, does a large force always cause a large impulse? And we're supposed to explain. So the simple answer, does a large force always cause a large impulse, is simply no, it doesn't. And we can explain that because impulse is equal to force times time. So just because we have a very large force doesn't mean that the product between force and time is going to be very large as well. All we have to do is make time very small, and that will neutralize the effect of having this very large force. Okay, so that was kind of easy on that one. Okay, so number 10 says a 15 Newton force acts for 8 seconds, and we want to find out how much momentum was gained. So remember that how much momentum is gained is basically delta P, change in momentum, and that's equal to impulse as well. Impulse is equal to force times time. So 15 newtons times 8 seconds is going to be equal to 120 kilogram meters per second. Okay, so number 11, we want to find out how much momentum was gained by the 4 kilogram object, which I have actually put off the screen, but you can see it there. For the first object, the momentum is 36. After the collision, or after the application of force, momentum was actually before it was 12. Afterwards, it was 36. So that's a difference of 24 kilogram meters per second. So that would be that. B, how big was the impulse acting on the object? Well, that's kind of our answer, because remember, impulse is equal to the change in momentum. So that's going to be equal to 24 kilogram meters per second. Calculate the time the force acted. Remember, not only is impulse equal to delta P, but impulse is also equal to force times time. And we know that impulse was 24 kilogram meters per second. And we know that the force was 8 newtons times time. So if we solve for t, we find out that t is going to be equal to 3 seconds. So that was pretty easy. And then calculate the acceleration of the object. Whoa, sorry about that. Force is equal to mass times acceleration. So the force was 8 newtons. The mass that was given to us, that was 4 kilograms. So the acceleration then, if we solve for that, that's equal to 2 meters per second squared. And finally, what is the final velocity of the object? The momentum after is equal to the mass times the final velocity, or the velocity after the application of the force. So 36 is going to be equal to 4 times the velocity afterwards. Solving for the velocity afterwards, or velocity final, that would be 9 meters per second. Okay, for this last set here, we need to find out if the collision is elastic, inelastic, or perfectly inelastic, and some of these could be more than one. So for letter A, we have that the total amount of momentum before is equal to the amount of momentum after. So momentum's conserved, however, kinetic energy is not conserved. So it can't be elastic, but it can be inelastic or perfectly inelastic. Here, kinetic energy is equal to kinetic energy after, so that has to be only one thing, that has to be an elastic collision. For C, the momentum before is equal to momentum after, and the mass afterwards is equal to the mass of object 1 plus object 2. So that means that things are sticking together, so this has to be perfectly inelastic. There's little or no sound, so if there's little or no sound, that means that most of the kinetic energy is conserved, so this would be elastic. If there's lots of noise, it would be the opposite of elastic, so it would be inelastic or perfectly inelastic, either one, because kinetic energy in both of these is not conserved. And the same thing goes for objects that are mangled or crushed. Remember, elastic, they keep their shape, they're not deformed. In both inelastic or perfectly inelastic, these two are certainly options. Okay, really quickly here for number 13, two objects collide but they don't stick together, so this is not going to be an inelastic collision. What happens to the momentum of the 4 kilogram object? Well, that is going to obviously increase. Okay, what happens to the momentum of the 6 kilogram object? That would be the opposite. If one increases and we have to conserve momentum, the other one has to decrease. And what happens to the total momentum of the system? Once again, it has to be conserved because that's the law of conservation of momentum. So we can say it's conserved, aka it stays the same.